My name is Takeshi Shinohara. In this presentation, I'd like to talk about pivot selection for narrow sketches by optimization algorithms. Our interest is in similarity search in metric spaces. Multimedia data, such as images and sounds, are represented by their feature data as points in a high-dimensional metric space. In information retrieval targeting such high-dimensional data, search by exact match is not effective because it is affected by the curse of the dimensionality, and therefore similarity search is required. Known methods for fast similarity searches include tree index and dimension reduction and locality sensitive hashing. In this research, we deal with sketches which are considered as images of locality sensitive hashing. Sketches are compact bit strings representing data points. The transformation that projects points onto sketches can be seen as a kind of locality sensitive hashing. Hamming distance is the typically used distance between sketches. Due to a lack of information, the distance between sketches is used as a priority in filtering to select solution candidate. The k-nearest neighbor search using sketches is performed in the following two stages. In the first stage, we roughly narrow down to k-prime solution candidates by filtering using the priority of sketches where k' is larger than k. In the second stage, we use the original distance between points to find the top k neighborhoods points out of the candidates. Search with sketches has a trade-off between accuracy and speed. The length of the sketch, that is, the number of bits, is called the width. If wide sketches are used, filtering will be slower, but accuracy, that is the recall rate, will be higher. And the number of solution candidates k' can be reduced, so the second stage search will be faster. Conversely, with narrow sketches, filtering is fast but inaccurate, and second stage search are slow. The main purpose of this study is to increase the search speed, that is, reduce the total cost of the first and second stages. If we want to speed up only the second stage, we can use a wide sketch, but doing so slow down the first stage. In this way, the balance between the first and second stage is important. Here I explain our previous achievement related to this research. Unlike local search, simulated annealing can obtain a global optimal solution, but it generally has a problem of high computational cost. In LWDA 17 and ICPRM 19, we proposed AIR as an efficient implementation method of simulated annealing. In ICPRM 18, we proposed priorities used for filtering that are more accurate than the conventional Hamming distance. We proposed score P, which aggregates the distance lower bounds in the same way as Minkowski's LP distance. Furthermore, in ICPRM 19 and AI 19, we proposed a fast search method using narrow sketches, such as 16 bits. One of the keys to this method is that sketches are enumerated in order of priority without matching to achieve fast filtering. We confirmed by experiments that the search using narrow sketches with the recall rate 90% can be performed about 28 times faster than the conventional method using the 32-bit sketches. In this paper, we propose a pivot selection method that utilizes the principle of speed up by narrow sketches. I think it is hard to believe that using narrow sketches enables faster searches. Here I'd like to explain only the outline of the key to the speed up. The conventional search method using sketches collates all the sketches of the dataset prepared in advance and filters them. We call this sequential filtering. On the other hand, in the fast search using narrow sketches, the sketches are enumerated one by one in order of priority without correlation. We will call this filtering by sketch enumeration. This table compares them. N is the number of data points, W is the width, and K prime is the number of candidates to be obtained by filtering. In sequential filtering, all the priorities are calculated. The cost is order of NW. In contrast, filtering by sketch enumeration does not require priority calculation. The number of sketches to be enumerated is 2 to the w's power multiplied by the ratio of k prime for n. This cost is an exponential with respect to w, but in reality, this cost is very small as long as w is not very large. We can use the bucket method to manage the dataset indexed by narrow sketches such as 16 bits. Because the number of narrow sketches is not very large and the arrays representing the bucket fit in the main memory. Therefore, we can very quickly execute the nearest neighbor search by combining the bucket method with one-by-one enumeration of sketches in order of score. The contribution of this paper is that we have achieved a further speed up of the nearest neighbor search by pivot selection. Pivot selection is to find a set of pivots that hires the recall of the nearest neighbor searches. The conventional method performs optimization using an indirect evaluation measure. Indirect evaluation measures include collision probability, entropy, and distance information loss. The proposed method optimizes pivots using the recall rate of the nearest neighbor search itself as a direct evaluation measure. I will explain the pivot selection method we propose in a little more detail. Pivots are selected using training by optimization algorithms. We use local search and simulated annealing. For simulated annealing, we use AIR developed by us. The recall of the nearest neighbor search is used as the objective function. It is efficiently evaluated based on the fast filtering by sketch enumeration. In our previous experiments, we used only in-house image feature data. This time, we also use the publicly available recaf descriptors data. This slide shows the outline of local search. NB of P is the neighborhood of P. It starts with any couple of pivots. It iterates improvement trials. In each trial, it randomly selects P prime from the neighborhood. If P prime is better than the current P, then it moves to P prime. We use AIR as an efficient implementation of simulated annealing. Air behaves very similarly as local search. The difference is that air uses a resampling of queries. The size of resampling gradually enlarged. This is corresponding to the cooling, the temperature, in the usual simulated annealing. In trials corresponding to those in high temperature, air uses small resampling, for which evaluation costs are very small. This derives the main merit of air. We use two datasets in the experiments to demonstrate the effectiveness of the proposed method. The first one is the image feature data of the in-house used in our laboratory. The other is the Decaf descriptors of images published by Professor. The number of data points is 6.9 million and 1 million, respectively. Dimensions are 64 and 4096. The distance functions are L1 and L2. Score 1 and score 2 are used as the priority of filtering. For the narrow sketch widths, 18 bits and 22 bits are used to achieve the fastest search. We use the training examples and the test cases shown in this table. The number of data in the training example is 1/60th and 1/8th of the entire dataset, respectively. The reason why we do not use the entire dataset is to prevent overfitting and reduce the cost of pivot evaluation. As for the query example, the training example and the test case are disjoint. The test cases use the entire dataset for both image and Decaf. This table summarizes the optimization process. The sketch filtering performance is expressed as the ratios of K prime to N that achieve recall rates of 80% to 95%. The smaller this ratio, the higher the filtering performance. We ran experiments 5 times and the average values are listed. The reason why the number of local search trials is small is that not only does it take longer to optimize than air, but the results do not improve even if the number of trials is increased. Probably because local search falls into a local minimum solution. Air, like normal simulated annealing, needs to increase the number of trials to get a good solution. For the image dataset, we have been able to obtain a fairly good pivots in 1 million trials. Since the CAF data has a higher dimension than image, the width of the sketch is as large as 22 bits, so filtering by enumeration is a little slower. And therefore, the calculation time for optimization is longer. In both cases, the pivot found by air shows the best performances. The search speed using these are shown in the next slide. Finally, we compare the speeds of the nearest neighbor search before and after applying the proposed method of pivot selection. First, as a reference, the average search time per question of a simple method that does not use sketches is set to the exact line in milliseconds. The image requires 114 milliseconds and the Decaf 625 milliseconds. Of course, the recall rate is 100%. For the search using sketches, the accuracy is set to 90%. Sequential filtering uses 32-bit sketches of the pivot selected by QBP to reduce the collision probability. In filtering by sketch enumeration using narrow sketches, Even the ones obtained by QBP are speed up for the smidge, the curve, up to 3 milliseconds and 47 milliseconds respectively. The last line is the search using the pivot that was selected to maximize the recall by air proposed in this paper. The search speed is almost doubled. In this paper, we proposed a high-performance pivot selection method using a direct evaluation function that breaks the limits of optimization by an indirect evaluation function. Using narrow sketches designed by the proposed method, we have succeeded in further speed up of the search. One of the feature subjects is to improve the efficiency of sketch enumeration. We have already devised a constant drift algorithm for Hamming distance and score infinity. In the current algorithm, enumeration in the order of score 1 and score 2 has an order of log n delay. If we can improve the enumeration for score 1 and score 2, we expect the search will be even faster. In the demonstration experiments so far, datasets, sketches, and buckets with sketches as keys, and so on, are all performed in the main memory. Therefore, establishing a search method for datasets that are too large to fit in the main memory is also an important feature subject. This concludes the presentation.